Hey everyone, I wanted to give you a brief introductory video on what we're going to be looking at in your activity today, where you're playing with a molecular geometry simulator. This right here is called molecular geometry, and it's referring to the three-dimensional shape of molecules. You could find the textual support in chapter 10 of your Silverberg textbook. I know I've showed you this picture before, but what this represents, back in 10th grade, what this represents here is HIV protease, which is a protein that is part of HIV infection. And what this represents in the middle here is a buckyball. And buckyballs are a 60 carbon spherical shape that is pure carbon. And what this is suggesting is that molecules like buckyballs could be designed perhaps to fit in the active site of a protein that's doing bad things. And if the substrate that we provide, a drug of some sort, binds competitively with the bad enzyme that's doing harm to us, it's possible to mitigate or even stop the progress of a disease. And all of this is based on three-dimensional interactions. The theory that we're going to be looking at and using is called VSEPR theory, and VSEPR stands for valence shell electron pair repulsion model. And what this means is electrons are negatively charged, and the electrons that are surrounding a central atom have an effect on one another. The premise: the bonded and non bonded electrons around a central atom in a molecule repel one another. Therefore, molecules adopt 3D geometries in which auxiliary atoms or groups, those are the groups or atoms that are surrounding a central atom, they spread out in 3 dimensions around that central atom in an effort to minimize electron-electron repulsions. And this is why you get the structures that you get. We study, if this sounds a little familiar, we studied it in 10th grade. And I'm going to show you a video here that I have previously made that illustrates this concept. So this video here introduced a very simple example of a linear molecule, but now we're going to be expanding into much more complex shapes. What you see here is the traditional Lewis structure of water on the upper right-hand corner, and it's always represented in this V or bent shape. And the reason, even if the illustrations don't show the non-bonded pairs around the oxygen, even when those are omitted, you'll still see water represented in this bent shape. And that's because lone pairs around a central atom are also repulsive. And in fact, lone pairs are even more repulsive than bonded pairs. Let me show you what I mean by this. Here's an image of water that I'm flipping around in 3 dimensions. Notice that when you include the non-bonded electrons around the oxygen, this actually makes a tetrahedral shape with angles of roughly 110. If non-bonded electrons didn't matter, water would simply adopt a linear shape if only the bonded electrons going to and from the hydrogens mattered. So what we're going to learn moving forward is that it's very important to consider the non-bonded and the bonded pairs around a central atom. What's also interesting is that instead of adopting the perfect tetrahedron, for example, if we were looking at methane and this instead of oxygen were carbon bonded to 4 hydrogens, you would get a perfect angle of 109.5 in all directions. But interestingly, non-bonded pairs are actually more repulsive than the electron pairs and bonds around the central atom. And what this does is this distorts the perfect tetrahedral shape because the non-bonded repulsions are stronger than bonded. This angle actually shrinks in water to less than 109.5, and this angle expands to greater than 109.5. Another thing I wanted to point out from the previous example is that because double bonds, even though they contain 2 pairs of electrons or 4 total, because they're going to and from the same element or elements, for example, if we go back and we look at the carbon dioxide, because these 4 electrons are going to and from the same 2 elements, they act as a single repelling unit. So when we're thinking about geometry, treat double bonds like you would single bonds.